so the next speaker is Katharina Kormann on structure-preserving particle-in-cell methods for the Maxwell-Vlasov equation. Please,
yeah, thanks. And yeah, I'm very happy to be here. Just arrived. And yeah, I'll talk a bit about the work we're doing at the Max Planck Institute for Plasma Physics. Yeah, with quite some people. We're interested in deriving a particle-in-cell method that also on the semi-discrete level preserve this plasma structure. And we had this discussion earlier. And yeah, so in this talk I will mainly focus on recent work on putting things to curvilinear coordinates, where magnetic pairs graduate school student is heavily involved. Okay, so let's look at equations. So we look at the non-relativistic Vlasov equation, not Vlasov-Poisson as in the talk before, but Vlasov Maxwell. So we have this transport equation up there. There's no point or something. Okay, so we have this transport equation, and we have a nonlinear coupling to the fields, to the Lorentz force in the transport equation, and then here you see the Maxwell's equation, and you have the source terms, the current and charge density, which are the moments, velocity moments of our distribution function. So here we have this nonlinear coupling. And yeah, we have the characteristic equations, which are becoming important for the Vlasov, for the particle-in-cell method, where you let particle represent your distribution function that evolve according to these characteristic equations. Yeah, and then there's a lot of structure in this system, and the idea is to keep as much structure as possible into your numerical method. Yeah, so just a recap, I think we had many things on that already in Erwan's talk. So yeah, as the most important conservation properties, I name we have energy, momentum, and charge conservation. Yeah, then if you look at this Hamiltonian of the system, so we have the kinetic energy and the potential energy, and that this energy is conserved over time. Yeah, then looking at the Vlasov equation, the Maxwell's equation, so we actually don't solve the full system, but we only solve the amplitude, and they possess a unique solution in time. And yeah, and on this continuous level, you have these divergence constraints satisfied over time, given you have them satisfied at the beginning. And now for your numerical scheme, of course, you would like to have that too. And what is behind there is this Dirac complex structure. So you have your fields and source terms in this Dirac complex. So you have the potential in the first zero form space. Then you have your electric field in this one form space, the magnetic field in the two form space, and then you have the charge density down here. So this is a formulation. You can also flip it. You can have some dual formulation, or you would swap those spaces. But that's the way we use it. And then you have this exactness property. So since the divergence of a curl is zero and the curl of the cut is zero, due to this exactness properties, you will have those divergence constraints satisfied. So this is the structure behind, in a nutshell. And based on this, we have designed this, what we call GEMPIC, Geometric Electromagnetic Particle-in-Cell Framework, where the idea is that you use, for the fields, finite element exterior calculus. You use conforming finite elements that form a commuting diagram with your Dirac complex. And you use just particle-in-cell in space. And then we have formulated the equations of motions, the semi-discrete equations of motion, by putting these answers into the Poisson bracket and derive discrete or semi-discrete Poisson bracket, that actually satisfies still Jacobi identity. Then you have to, of course, go to the spatial, to the temporal discretization as well. And there in the original paper, we used the Hamiltonian splitting. So you split the Hamiltonian, similar to what Aaron showed us earlier. So you have different parts that you solve. And for this Cartesian grid that we had looked at there, we could solve then the subsystems exactly. So we had a symplectic method. Then recently we have looked into doing this with energy conserving time discretization instead, and use methods based on the discrete gradient. And we get back to those for the curvilinear context in this talk. So yeah, so far this was on Cartesian grids. We only considered that so far. I work at the Max Planck Institute for Plasma Physics, so we don't want to look at the academic toy problem, but maybe at the tokamak. And tokamak looks in a simplified version, something like that. So yeah, we need to have some coordinate transformation. We have to transform to a real domain. And that is what I at least partly address in this talk, to go to a curvilinear description of our coordinates. And if I have some time left, depending on how long it takes, I will also talk about how to, because you see here we have angular dimensions. So if you have this transformation, we have the radial, but then we have an angular coordinate, and their Fourier methods are typically also used in plasma codes. So we also want to include a Fourier description along some directions in the problem. Okay, so then let's talk about this curvilinear version. And here I first give a bit of notation that I will work with. So so far we have always assumed we have a transformation f from the logical space in 3D to our physical space that is invertible. So we don't allow for singular points for the moment. So we can write down the Jacobian matrix, and based on the Jacobian we can define the covariant basis, and then the contravariant basis is defined by the inverse Jacobian. And then we will also use the metric. So here the metric for covariant basis denoted by GT, and the basis for the contravariant metric for the contravariant basis denoted by Gn. Okay, now we have this differential form, so we have to take care how we transform them. So for this third form is you have the zero form, so the first space in the diagram complex. These are scalar functions, and in this case, we just define the curvilinear version as put in the coordinate transformation. But then you have to take care, if you now go to the one form, how do you get from a zero form to one form? You take the gradient. So, and when you take the gradient between the physical space and the logical space, then you get this the contravariant basis factoring here. So a one form, and here you use E because it will be the electric field. These are one forms. We have a vector transforms with this transposed inverse Jacobian n of psi. Then you can go on with the two form. You take the curl, then here you get this the df, so the Jacobian divided by the Jacobian metric, the Jacobian determinant, and then finally for the three form you get the 1 over the Jacobian determinant. So when we formulate things in the curvilinear sense, we of course have to take care of these transformations. And then we have to apply this to our equations first without numerics. if we transform Faraday's law, then on the right side, we have the curl of the electric field. When we have the curl, then we get this that we just had before. If you compute the curl and transform it from the physical to the logical coordinates, you get the df of psi divided by jf. But then on the other side, you have a 3 form, and the 3 form transfers exactly with the same factor. So in that case, they just disappear. The same thing here for Gauss' law. Okay, there the right-hand side is 0, so we can just take out this Jacobian determinant. I mean, it's true anyway, because we have no singularity. Ampere's and Gauss' law, now we have to look at in weak sense to make sense of them. So we have a mixed finite element formulation that we need to apply in this case. And then we do this. It's a bit technical. You have your weak form of Ampere's law, for instance, in the first line. Then, okay, these are H curls, so we have to do this transformation here according to a 1 form. So that's all in the first part. Then again, we have to take for the curl, we have to take the df and here also this jf, but we get it twice. But then we also have the transformation of the integral. So the right stays 1 times the denominator. Okay, so you put it in, and you get some a bit more complicated equations, but you can write it down. You have symmetrics inside, and then you have the formulation where you can do your discretization, because we want to have a discretization that we put in this logical coordinates. Okay, so then of course we also have the Vlasov equation. Also here we need to account for the curvilinear coordinates. Again, here we have derivatives popping up. We transform to the logical fields in the logical coordinates, and then we get this equation. And from that, of course, we get our characteristic equations, which we formulate now in a mixed form. So we have the characteristic equation for the logical point in space, but we keep the velocity, the velocity that belongs to the physical space. So here we don't transform to logical space, because otherwise this transformation here would be, you would need to have Hessians inside and a complicated structure. So we have this mixed formulation, but then of course here we need this to account for the fact that that's not the velocity in the same space. So the equation here gets a bit more complicated. So it's not conjugate variables that we use here. Okay, based on this formulation in curvilinear coordinates, we do the spatial semi-discretization. So we use particle-in-cell. So what we do is we write our distribution function as a sum over all particles. So we have a number of particles that we distribute. Each particle has a weight, omega p. This is constant over time in that formulation. And then we take a delta distribution. So we say these particles have just a delta weight. And this is well defined because we use those equations where we have the source terms in weak form. So we have in the Ampere's law, we have on the right-hand side to integrate over our velocity times the distribution function. And since we then test that with our test functions, we can just evaluate the test function at the positions of our particles. So we don't have a problem with this delta point sources. But you could think of a smoothing, just put the particle, some smoothing kernel around the particle. You could also do this, would work as well. But then the formulas get a bit more complicated. functions here. And then, yeah, again, here we have to make sure we do the transformation correctly, so then we get this Jacobian determinant here in the denominator, but otherwise it looks the same. And then, yeah, we can compute here our right-hand side for Ampere's and Gauss law. Yeah, we have to plug in these expressions here for the logical coordinates. If we do this, our characteristic equations look like this. So we have now the vector big psi, capital psi, that's the vector that contains all the positions of the particles. So first 3 positions of the first particles, and the second, and so on. And then we have this, math BBN here. So math BB always indicates here we have a vector over all particles. Yeah, so and these are typically Bloch matrices. So we have here a transformation on each particle. So this is an equation for each of the 3 coordinates of each particle. There's a coupling because you have to transfer from the physical to the logical velocity of the particle, but it doesn't couple between different particles. So it's a Bloch structure that you have in here. In the same way for the velocity, you also get this transformation by the Jacobian inside, and then you get here the Lorentz force. Yeah. Okay, so well, they get a bit more complicated. I will also see then later on. This will get a bit more implicit than if you do it on a Cartesian grid or with an orthogonal transformation. But you can still write it down and handle it. Now we have to go to the fields. We have to discretize them. And for the method without curvilinear coordinates, if you have Cartesian grid, then you can quite easily design such structure preserving finite element spaces based on this finite element exterior calculus theory, where you have a commuting diagram between your numerical spaces and the continuous spaces. And there are several such spaces, but the one that we have used and that we rely on is based on splines. The reason is that the splines are smooth, and remember we had this, we say that a particle is a point particle, and then we just have we tested it with the test functions, with your finite element functions. And if they are smooth, you have some kind of smoothing in there. So that's why in this context, it's a good idea to use the splines, which have some higher order splines, also not linear splines. So typically we use third order splines. So you have some kind of smoothing effect in your method. And so the idea of this the RAM complex based on splines is that you start with some order. So we're in 3-dimensional space, so we do a tensor product of 1-dimensional splines in each direction. For simplicity here, I assume they all have the same order from the start, but they don't have to. So we could start with different order in different directions. And then going from the 0 form to the 1 form, what you do, you take the gradient. So then in the first component, so now we get a vector valued function. In the first component, we take the derivative with respect to the first component, and taking the derivative of a polynomial, the degree decreases with 1. And that's like a really nice way to construct this RAM complex. It's an exact complex, so you have the nice properties that you like. And it's easy to construct that on this tensor product, right? And now the idea is, of course, in the logical space now, there we have this property. Yeah? So we use those splines in the logical domain, and then we transform them to the curvilinear domain. And so to make it a bit more explicit, what that means to have the complex on the discrete level. So if, and I write it down now in the logical coordinates because it's there where we can simply construct it. Yeah, we take a zero form, we take the derivative, we take the gradient, and that is the same as writing you have to end up in your basis of the one forms times some matrix that I call G, the gradient matrix. In the same way, you have such an identity for the curl between the one form and two form, and the divergence for the two form to the three form. And we have G, C, and D. And if we have now this, we have such basis functions that satisfy such an identity, where in addition we have that D is the transpose of G matrix, and D times C and G transpose, which is the same as G transpose C, is 0, and C times G is 0. So this is the discrete version of the exactness property, def curls equals 0 and curls equals 0. And now, suppose we have this. So this you can write down for the spline, finite element your calculus complex, and yeah, you have those matrices. They're very simple. They have some ones and minus ones on some diagonals, and then you plug in your formalism of coordinate transformation. Then you can see that you get same property on the physical coordinates. So assume, just let us look at the first line here. We take the gradient in physical space of our zero form basis. Then we can transform to the logical coordinates by having this transformation rule for the gradient. So we get the df minus transpose in here. Then on this discrete level, if we dare, on the logical level, if we then have this property of the round complex, so yeah, we apply this to the back part. So we have this equation, and now we see that this here is exactly how the one forms transform between the logical and the physical domain. So what we have, if we look at that first and the last thing in this equation, we have exactly the same property in the physical space. So this construction, if you do it properly, all those properties transfer to the physical space. You can go on with the other identities. And so we have to note that these matrices, the discrete gradient and the curl, they look exactly the same in the logical and the physical space. Okay, so yeah, so we make the ansatz for our logical fields now with the one form for the electric field, two form basis for the magnetic field, and then we can plug in this into our equations that we have derived for the curvilinear form of Ampere's law and Faraday's law. And yeah, it's a bit, it's a bit technical, but in the end you get nice equations here, which again contain in addition these matrices and of the side vectors. And what you can do is you can also show that the Gauss laws are satisfied. So yeah, you put them in, and yeah, you get some equations here as well. So to sum up, the discrete Hamiltonian looks this way. So we have the kinetic part, which is simply V transpose V with in the middle a matrix that contains the mass of a particle and the weight of the particle. Yeah? So this is really just a diagonal matrix. So it's not, we will see some inversions of these MP or MQ matrices. This is nothing that is problematic. I mean, this is a big matrix, but it's diagonal, so you can simply write this And then we have the field parts. There we have the mass matrices, so the finite element mass matrices in the Hamiltonian. And with that, you can write down the semi-discrete equations of motion. So we have them on slides before for how the position and the velocity evolves and how the electric and the magnetic field evolve. And yeah, so these are the equations that you actually solve. And what I do here is if we just take the D matrix and apply it onto Faraday's law, we can show that the divergence constraint for the magnetic field is satisfied. And in the same way, taking the G transpose, which is also the D matrix of Ampere's law, we can show that the Gauss law is satisfied. Yeah, so these two equations, they come due to this property. I mean, this part here, for instance, vanishes because G transpose C times G is equals to 0 because of the exactness property. And you have that on this matrix level. And then you can write everything together in this Poisson structure. So you can write it as a Poisson matrix times the derivative of the Hamiltonian with respect to the dynamic variables u. So u collects the position, velocity, and the degrees of freedom, finite element degrees of freedom of your field description. Yes?
Can I ask a question about the Gauss law on the previous slide?
Yes.
So the second one, is that only satisfied weakly? Is this transposed with respect to the finite
Yes.
element mass matrix, not?
Yes. So you have you have this formulation where you have the terms with where you have sources. So the Ampere's law and the electric Gauss law, those are only satisfied weakly.
Oh, okay. But the first one is strong, right?
The first one is strong, as well as Faraday's law is strong.
Right. Okay. Great. Thanks.
But that's how it comes out if you have this formulation, and then, you really get those equations that you get in this formalism set.
Okay.
The discrete electric field doesn't belong to H div, so its divergence is certainly not 0.
Right.
It doesn't have a divergence.
Yeah, exactly. And just making sure that this was the usual thing.
Okay, so we are in this form, and we can write down how the Jacobi identity looks like or should look like in terms of this Poisson matrix. And yeah, it's a bit of tedious calculations, but you can show that it's actually satisfied. So here we really have, at that level, we have the Poisson structure still there, preserved on the discrete, semi-discrete level. Okay, so then we have to discretize in time. And yeah, so we look at these different variants that we have used without coordinate transformation, and yeah, some of them get a bit more complicated, of course, when we use a coordinate transformation. And so remember about the Hamiltonian splitting. What I told you is that for the case where we have no coordinate transformation, we split the Hamiltonian, and we split it enough so that we could solve all the resulting systems analytically. And in particular, this is a problem for the kinetic energy part. So what is HP here? So what you see here is the system that comes out if you plug in your Poisson system just a part of the kinetic energy. You get this system of equations. And here, this is non-linear because here you have the update of the position, and of course the update of the position comes here on the right side, and also here. So yeah, you cannot just integrate over it and solve it. While those two systems here, they are really linear. So you have here an update of the velocity, but the velocity never appears on the right-hand side. Here we have an update of the magnetic field, but it doesn't appear on the right-hand side. So you can just integrate over it. And the same here, we just update it without any dependency. So these two systems are simple to solve. The first system is a bit harder. And what we did when we don't have a coordinate transformation then I mean it's still would be still non-linear in here. I mean we wouldn't have this term, but still here for the velocity update, for the position update you need the velocity, and here for the velocity update you need the position. But you can decouple it by splitting the kinetic energy in 3 parts, each of one for one direction at a time. And when you do the splitting, because I mean here this is essentially the V cross B term, but in the V cross B term, in the first component, it's not depending on V1, so the dimensions separate. And then you can really integrate over them exactly. You do a little more splitting error, you have then 5 parts, but still each part can then be solved exactly. But that's not true anymore here. So here we have to really do some approximation. So this is the E and B field. As I told you before, you can just integrate it up. But here we have, it's a bit harder because we have this coupling between all the dimensions, so we cannot really split them anymore. And in that case, we use now a Kraus-Nicolson method. So yeah, we do just an implicit method here. But as I told you earlier, these methods are block diagonal. So the coupling is only between the 3 dimensions of each particle. So if that would be implicit in all the particles, because the number of particles is huge, you don't want to invert really matrices on that level. But since it's only on the level of the 3 coordinates for each particle, so you can solve this, it's not too expensive. So, yeah, so that can be done. It's moderately implicit, it's still quite quick, and the good news is that Gauss' law is still conserved. So using a Nicolson here does not destroy the property of Gauss conservation. Then, as I said, we were also looking at the implicit method, energy conserving methods. We designed something based on the average vector field method. Since we didn't want to apply this to the whole system, because again, this would be heavily nonlinear, what we do instead is to say we split the Poisson matrix. And what is important, of course, to be able to apply the average vector field method is you need to have an antisymmetric matrix. So the splitting has to be antisymmetric. So always you have to, I mean, you see here, this is the maximum splitting that you can do. So you keep somehow this antisymmetry, and you can split it in 4 parts. And then for each of the parts, you can use an average vector field method to discretize. Well, you have to do a little bit of nonlinear iterations here because, again, you have in the first line, you have this dependence of this n matrix on psi. So here we do some Picard iterations, but typically we need a few iterations. It's not too hard. And then you have, of course, in the third system, if you look here, there you have a nonlinearity, which includes both particles and fields. So you have the velocity, and you have the electric field on both the right and the left-hand side. But here we use, so this was system 3. Here we use a Schur complement in such a way that we only have an implicit equation on the field degrees of freedom, and I have to say that the field degrees of freedom are way less than the degrees of freedom of the particles. Yeah? So then we are fine with this. We solve the linear system, and then we have an explicit update of the velocity coordinates. So we don't have to do anything implicit in the fields. In the fields we have, but not on the particle level. The price we have to pay is that we have to, compute this Schur complement matrix, and this is a bit more expensive because it involves a tensor product of splines. So you have double the evaluation of splines. So instead of having a 3 loop over all your splines in each of the 3 directions, now you have a nested loop of 2 times this rate. So it's way more expensive. You can feel that. So it's not exactly as cheap as an explicit method, but it's moderately still the non-linearity in that version. But one thing was that in this, with this energy conserving method, we lose the conservation of Gauss' law. So the question was, could we do better? Can we change it a little bit? And so we still want to stay in this discrete gradient formalism of designing an implicit method, energy conserving method, but can we define the discrete gradient a bit differently so that we, on top of having energy conservation, also conserve Gauss' law? And indeed, this is possible. Now, what you do is, on the first level, when you do the splitting, you have to change the splitting and keep the update of position together with the force system. So the update of velocity and the source term in Ampere's law. So that's important. That the source term has an update in the same way as the position update. So you have to, you cannot be as aggressive in the splitting. But this gives you, of course, something that results in something that is a bit more non-linear. And also, you cannot use the average vector field method to construct your discrete gradient, because that in itself also destroys Gauss' law. But you can do it a bit different in that way, as you see here. Important fact here is that you use here something that is constant over time. The derivative is constant over time and can be plugged in here. And so you don't do this typical integration that you have in the average vector field method. We don't have that on this part. So we only do this on parts of the right on the right hand side here. And in that way, we managed to have a scheme that also preserves Gauss' law. But it's more nonlinear here, because now you really have a nonlinearity between the fields and the particle degrees of freedom. So here you have to iterate several times over your whole particles, which is of course way more expensive. Because also in terms of implementation, if you want to do an implementation here, you have to load your data. That's what is expensive. And here, of course, if you go through all your particles several times, you have to load them several times. So yeah, it's more expensive, but it can do more. So yeah, it depends on the problem that you have that you want to study. You have to choose which of the methods you would like to use. Just a few numerical. So I think I'm almost out of time, right?
You have 7 including questions.
Okay. So then just a quick overview of some results here. So we were looking at 2 different coordinate transformations. So far, we didn't look at boundaries. So we still have periodic boundaries. So we still have conservation. Then we have to, if we go away from periodic boundaries, we have to look at the flow through the boundary. But just to see if this coordinate transformation business works, we have looked at those artificial transformations of the grid, one called orthogonal transformation and one collider transformation. And we have looked at this initial distribution. So we have a Gaussian, essentially, with different velocities in different dimensions. And here you can study a linearized problem, which gives you growth rate here, the flat line for the field. So you can in that way validate if your results are correct. And yeah, we see that we follow that line up to a certain point, and that's then called the nonlinear phase. That's when nonlinear effects take over, and yeah, the growth stops because we do a nonlinear simulation. And we see like all the time-stepping schemes give good results. And now we look at the conservation. So we have the energy error, and there it exactly as said by the theory, if you use what we call here GEMPIC, so that is the version where you don't, where we have the Hamiltonian splitting, so we don't have an energy conserving method. And indeed, yeah, the energy is, I mean, it's not terrible, but there's an energy error, no matter of your coordinate transformation. If you instead use one of the energy conserving methods, this average vector field-based method, or the other discrete gradient method, you get conservation, but of course only it's a nonlinear method, so you have some solver elements in there that you see, of course. Again, if we look on the other hand at Gauss law, then now where would we expect that it's conserved for the what is just called GEMPIC, so the Hamiltonian splitting, and for this modified discrete gradient. And indeed, that's what we see. While the average vector field method, of course, yeah, has some violation in Gauss law. And again, we have a tolerance. That's what we see here. So the tolerance is at 10 to the negative 12. I think it's the tolerance we use, but of course, then we have some, yeah, the condition number of the matrix that increases it a little bit. Okay, so then one more point that we're addressing, as said, is to use a Fourier method. I don't think I have time to discuss that really, but I just give you a brief glance. So yeah, so you can also build a theorem complex based on finite elements defined on based on the Fourier modes. And the nice thing about this complex is that all the components of the different spaces have the same, yeah, and they're all Fourier modes, so they look the same. And in that way, it's possible to have very many conservation properties. Of course, we have spectral accuracy, so all these advantages. But if you do this, then you have also big disadvantages, because if you plug this all in, then of course your discretization means you have Fourier modes up to some big capital K, so it's the largest mode that you include. And then, of course, if you want to evaluate your field, say at the particle position, you have to evaluate the Fourier representation. So you have a global coupling. So for each particle, all modes have to evaluate. While with the splines, you had something which was local. So you just have a few splines in that area. And there we came up with something which is almost spectral, but local. And the idea is to approximate the Fourier transform by a discrete Fourier transform. And so the first step is so what you want to compute is your current density up there with the delta function, and then you need the Fourier transform, so you need to evaluate your E to the power ik at all the particle positions. But we take the convolution with a spline. And if you do this, if you look at Fourier space, a convolution is just the product. And then the Fourier transform of a spline that you know, it's a sinc function, so that you can compute. And then we didn't win anything because we need now the Fourier transform of that headed thing here with the spline to evaluate, and that's still expensive. But if we replace the Fourier transform by the discrete Fourier transform, then we get this formula. So what we do is, in 2 steps, we first evaluate our current density with the spline, and then we do a discrete Fourier transform, and there you can use FFT. So yeah, it's not exact. You have an approximation here, but what you do is something that is local. And you have actually quite a fast convergence. So you have convergence with order Q+1 to the real spectral case. So yeah, you can do it local and almost be spectral in a sense. So yeah, let me just sum up. Yeah, so what I showed you is how to design on a curvilinear geometry an energy conservative method based on particle-in-cells. And I showed you different schemes in time. And I also briefly mentioned that this can be enhanced with spectral accuracy for the angular coordinates. Yeah, so let me wrap up by saying, okay, there are some open questions, and of course I'm staying here for a few days now, and I hope to get some smart ideas from you. So one thing that we are interested in, of course, I mean, now I showed you just with this periodic domains and artificial coordinate transformation. So what we would be actually interested in is to look at boundary conditions. And also, I mean, you have a singular point in there which has to be treated. I mean, if you have the coordinate transformation, at least you have one in the middle. And then also with the temporal schemes, I know if there is some expertise here, so yeah, maybe this using a Crank-Nicolson, is that really the right choice? And then also going beyond what we have now. Yeah, we're looking a little bit into sub-stepping. So what happens if you have strong magnetic fields? Yes, it's this kind of splitting really a smart idea, or yeah, should one do it differently? Yeah, so I think that's the yeah, and then also of course an interesting thing would be to see how that goes with grid-based methods. So you were mentioning this error of semi-Lagrangian. Can one control this? Yeah, can one go back? Because parting methods are nice. You can do all this nice conserving schemes, but then you have a lot of noise. How can you handle that? Can you use some semi-Lagrangian schemes, or also I was looking to low rank methods, if that can be combined here as a control variate or something like that to improve on the efficiency also of the method. Okay, thank you.
Question? Christian?
You've shown us the Poisson structure in the semi-discrete system. Does it converge to the original Poisson structure if I remesh, if I make my mesh finer in any sense, or is it completely a new structure?
That's a good question. I haven't thought of that. So I would guess it converges, but it's a guess. I don't know. Yeah. But yeah, if you have some ideas how to do that.
Concerning the boundary conditions,
Yes.
Is it clear for physicists what it should be already, or?
That's a good question. Well, so I mean, at the first point, what we would look at is a case where you have like zero boundary conditions. So I mean, you have this is not going to all the way towards the wall of the socket, because then you would also have the X point where you have to do a multi-patch or something, and I mean then it's even more complicated. So this doesn't directly extend to that, right? But for the wall, I think it's not so easy. But so I mean, typically you do some entire kinetic simulations. They do this where they have like the gradients going to zero at the boundary, and they look at something that happens locally, localized somewhere. You have a gradient, the temperature gradient somewhere, and then you let it flatten out, and you put some kind of zero boundary conditions. But of course, I mean it's like a model, but you're right. I mean, studying boundary conditions is a complete problem in itself for the physicists.
Okay. We are quite way into the coffee break now, and but it's very interesting to have discussion. But I suggest that maybe we can discuss a little bit on the way and during the coffee break. And the next talk is at 12, I think, and the coffee break is in the main.
In the mezzanine.
Yeah. Okay.
So we go back.
That's right. Thank you again.